So this is just a very quick review for our exam 4 in this class. Could be an exam 3 in some other class, but our exam 4 with differential equations, where did we end with exam 3? We ended with section 3.4, I believe. We've just started learning about complex eigenvalues and eigenvectors and solving linear systems with complex eigenvalues and eigenvectors. That was 3.4. So there's the rest of chapter 3 since then. That has been, well, 0 eigenvalues and repeated eigenvalues. That was section 3.5, though we didn't do that right away. 0 eigenvalues and repeated eigenvalues. The repeated case was the harder case. The 0 case is the degenerate case. When 0 is an eigenvalue, you have infinitely many equilibrium points, typically a line of equilibrium points. But the methods that we use with eigenvectors and finding solutions still works. You can still diagonalize the matrix. The repeated eigenvalue case is the harder case. That's where you need the Jordan canonical form, which is tricky to try to find a matrix P that converted A to Jordan canonical form. You should know what the Jordan canonical form is for a 2x2 case. You're going to have, it's going to be an upper triangular matrix with the repeated eigenvalues in the main diagonal and a 1 in the upper right corner. The matrix exponential is relatively easy to compute in that case, though not trivial. Look at that on the take-home exam from a couple of years ago. This kind of problem comes up. Just quickly summarizing it. That is the harder case. We also did section 3.6 is the harmonic oscillator. Classification. I won't write down the classification. It's underdamped, undamped, underdamped, critically damped, and overdamped. The most important cases being underdamped versus overdamped. Trace-determinant plane. Bifurcations related to that. For linear systems. Also 3D systems we did briefly. The algebra can get nasty, so if I did a 3D system in class, I'd give you a lot of help. But the method is still pretty much the same with the book's method. Still find the eigenvalues, find the corresponding eigenvectors. They're going to be linearly independent if you've got distinct eigenvalues. So a general linear combination gives you a general solution that you can use to solve initial value problems. Yeah, if I put something like that in the exam, I'd have to give you a lot of help to avoid mistakes and save you some work and save me headaches with grading. But you should understand the idea and be able to do it if you had to with technology to help. Could be maybe more likely on the take-home if I did something on the take-home like that. Then we did chapter 4, forced harmonic oscillators. So initially, you do exponential forcing. We're more interested in sinusoidal forcing with, for example, cosine of omega t or sine of omega t. And even though you can solve it without complex numbers, I do want you to be able to solve it with complex numbers, to use the complex approach. Solve the corresponding homogeneous equation. That's chapter 3, really, but you don't have to convert to matrix form. Just deal with it in scalar form, but just write down the characteristic polynomial and find the eigenvalues. But then you also think about the force system, and you think about the corresponding complexified equation, where you have e to the I omega t on the right-hand side, and you guess something of the form a e to the I omega t for the yc. You find a as a complex constant. A itself is important because geometrically it's distance to the origin. its modulus, and its angle with the positive horizontal axis, also called the argument, tell you information about the amplitude and phase of the forced response, the YP. That'll be the real part of this if the right-hand side's cosine, and the imaginary part if it's sine, the forcing function. There is stuff that I didn't really talk about in class so much, but comes up in the book, came up in your homework, came up in the lectures about fast and slow oscillations when the natural frequency and the external frequency of the forcing function are very close together. You get fast oscillations in sort of like an envelope of slow oscillations. It's called the beating phenomenon, the beat phenomenon. And the complex approach is helpful for that too. Though you can on your note card just write down equations if you want for the frequency and the period if you like. There was stuff about analyzing things more generally and thinking about graphs of the amplitude and phase. I wouldn't have you calculate nasty partial derivatives like you did in your homework on the in-class at least. But you should understand it enough that if I made graphs, you would understand how to interpret them. Then we got into chapter 5, nonlinear systems. So that involves the usual things, nullclines, equilibrium points, and the new thing is linearization with Jacobian matrix, find the eigenvalues or do the trace-determinant plane. It'll be linearization will apply, Harmonic theorem will apply. Again, if the eigenvalues don't have zero real part, so they're not zero, so you're not on the trace axis in the TD plane. And you also don't have purely imaginary eigenvalues, you're not on the positive D axis. If you're down below the T axis or in one of the other two quadrants, you're fine. The Hartman-Grobman theorem applies. Linearization works. The new stuff about gradient and Hamiltonian systems today, for maybe true, false, multiple choice questions in the in-class, and maybe something more in-depth on the take-home. The idea of a trapping region is probably the most important thing from the extra reading. What about linear algebra? Had a lot with the matrix exponential. And powers of matrices. We applied that to both differential equations and difference equations via diagonalization. Diagonalization was the big overall topic. D equals P inverse AP is how you diagonalize A. That's equivalent to saying A is PD P inverse. One thing you can say is the matrix exponential e to the TA is P e to the TD P inverse. And A to the nth power is P D to the nth P inverse. These equations work even if D is not diagonal. They're just easier to use when D is diagonal, because that means these matrices in the middle are easier to compute. But D could be a Jordan form and they'd be harder to compute. Still possible. We also related this to coordinate changes, which I always remember as Y equals PU, which is equivalent to U equals P inverse Y. P is your change of coordinates matrix. It's implementing a coordinate change. And the system dy dt, for example, equals AY is equivalent to du dt equals du. And if D is diagonal, that's a completely decoupled system. And then the newest things have been about symmetric matrices. They always have real eigenvalues. There are always orthogonally diagonalizable. The matrix P can be chosen to be an orthogonal matrix, meaning the inverse of P is its transpose when P is orthogonal. It's got orthonormal columns, not only orthogonal columns, but they have to be normalized to be unit length to do this. And this is nice because transposes are easier to compute than inverses. And then the newest topic, I think in lecture 32A, also relates this to quadratic forms. Maybe that comes up at 31B as well. Quadratic forms. Final thing I'll say here are functions of a vector variable that have real number outputs. They're defined by taking the vector X transpose, so it's a row vector, times some symmetric matrix A times X. A is a symmetric matrix. And the key thing is you're interested in the quadratic form. Is it positive definite, negative definite, or indefinite? And it's related to the eigenvalues. What's the relevance for that for all the other stuff? I haven't said. Okay. This either comes up in 31B or 32B for the first time.